don't see the big screen before. Okay. All right, perfect. So another presentation as well is technology focused, so no products here related. I will talk about a completely new routing protocol. So we know routing protocols like OSPF version 2, OSPF version 3. We have some BGP routing protocol. We have ISIS as well. Maybe in some network we're still using IGRP or enhanced IGRP or maybe RIP and so on. So we have a couple of routing protocols. And I will talk about completely new protocols, and the question is why we need new protocol. Okay, we have so many protocols already, why do we need new protocol? So this new protocol is called RIFT, routing in fat trees. Okay, so let's discuss, some disclaimer as well at the beginning, that this is nothing in production, this is based on the drafts, on the standards. And let's discuss first, this new routing protocol is focusing on the data center environment, mainly. So it's focusing on very structured network topologies. So we know in the data center, the network topologies are pretty structured. So we have leaves, we have spines, maybe we have several layers of these leaf and spines, but every leaf is uplinked to the spines, spines on the next level are uplinked to the next spines, etc., etc. So it's very, very structured topology, as opposed to the topology that we observe in the network, in the service provider, for example. Yes, in the service provider topology, might be not very structured because it's restricted by the availability of the fiber. For example, I have fiber to this router, but I have no fiber to another one. I have DWDM here, but I have no DWDM here, etc., etc. So at the end, typically service provider networks are not so structured well as the data center networks. Okay, while we talk about the data center, we talk about DC because we are observing, especially in the so-called hyperscale DC environment. So what does it mean, hyperscale DC environments? It means that we have tens of thousands of the devices in the data DC fabric. So we observe that we are replacing layer 2 DC delivery with some IP-based fabric. And that's the reason here it comes new protocol in place. Okay, so hyperscalers in DC environment. So first of all, as I mentioned, so we're introducing the IP fabrics. So in these DC environments, we are using IP protocols as underlay, and of course, as overlay, we can run some layer 2 services. Could be EVPN, for example, as layer 2 service. Could be VPLS as layer 2 service, whatever is required, whatever is chosen by the operator of this DC fabric. And as well, we've seen sometimes in the metro environment, because of the caches, we see as well some designs in the enterprise networks as well. So sometimes in US, for example, educational space, we see the network designs that follow more or less the DC fabric designs. So we see this topology. And here, what is the characteristic of these topologies? They're uniform and regular. So they're very regular topologies. Yeah, we show some topologies on the next slides. So it's very regular topologies. And what we observe in the service provider network is that we are having plenty of traffic engineering and some protection mechanisms in place. In DC, this is not really used. So in DC environment, we don't use this traffic engineering or protection mechanism. Why we don't use? Because we have high degree of ECMP. So networks in DC environment, DC fabrics, are designed with high degree of ECMP, and then simply if one ECMP link fails, I have plenty of different remaining ECMP links to carry the traffic, so I don't really need to have some advanced traffic engineering or protection from that perspective. All right? And another thing is, when we go in the DC environment, we would like to have as less hassle as possible when we try to expand this DC fabric. So if you have your laptop or your server, and you realize that in your server there's not enough memory, what you are doing, you are going to the shop, buying some memory sticks, and put this memory in your laptop or your server, and that's it. You don't do any configuration. And the same idea is here in the DC fabric as well. So you have your DC fabric, you realize that capacity of this fabric is not enough, or you realize you have not enough access ports, for example. What they are doing, you are going to the shop, you're buying some switch, you put the switch in your DC fabric, and you don't want to configure that switch. Okay, so this is the same idea here. So configuration-less expansions of the DC fabric. This is what we try to achieve here as well. So let's go to discuss. So how DC fabrics are built, or how DCs are built. So this is based on the very old technology in internet terms, yes, from 15th, that was used in the telephonic crossbar. So in therefore telephonic crossbar scaling introduced by Bell Labs systems, so part of AT&T. So basically this is several stages. That was the input, that was the output, and here there were telephony access lines connected to these stages. And we follow exactly the same in the DC environment. The only difference is that we are folding this input. So in the telephony we had separate input and separate output stages, levels. Here we are folding that together, and in our DC environment, these guys here, they are input and output guys, so to say. They are leaves. We can accept the traffic, and we can send the traffic. Okay, and this is typical DC fabric environment. Depending on the size of this DC, we could have many more levels. In the small DC networks or DC fabrics, we have 2 levels only. Yes, we have leaf level and spine level, but we could have more levels. We could have 5, 6, 7, 10, whatever number of levels. It really depends on the fabric size. So if you think about the fabric sizes that is used by Facebook, for example, by Apple, Oracle, or these guys, yes, they have much more levels than 2 or 3. So I can assure you. As you see here, this DC fabric is very regular topology. Yeah, we have very regular topology, as you see on the previous picture, and very high degree of the connectivity. So typically, okay, on this picture I didn't show very high degree of connectivity, but typically here we have like, 10 uplinks or something like that in the large networks. So very high degree of the connectivity. Well, the current protocols, they are built to handle irregular network topologies. Yes, you have some irregularity can be handled by the current network protocols, and as well they are built with they are not optimized for the high degree of the connectivity. So if the low degree of connectivity, it's okay, but not the nice high degree of the connectivity. And as well, we have 2 kinds of protocols. We have link state protocols and distance vector protocols. With link states, they are very fast. This is OSPF or SIs, for example. They are very fast, but they're not very scalable to the large number, like 100,000 nodes. Okay. And as well, we have distance vector or path vector in case of BGP. They are scalable. We know BGP is deployed worldwide, so they're scalable to a very large number, but they're not particularly fast. Yeah, if we like to achieve like 50 milliseconds failover convergence with BGP, that could be challenging. So, small review. Link state protocol. What is link state protocol? So basically, link state protocol is every node in the network announces the information, local information. So what links are connected to my node, what prefixes are attached to my node. This kind of local information is announced, and this kind of information is flooded through the network. So which means every node in the network has the same information about the network. So this is the link state. And based on this information, every node in the network can build the topology view of the entire network, okay? Because everyone has at the end the same. So this is the link state. And what is the advantage of this? Well, the advantage of this is that it is very fast when it comes to convergence, yeah, because every node has already all the information of the network. The same information is already presented. If the link fails, I can very quickly recalculate that. But has some disadvantages. And what are the disadvantages? Well, when the networks start to grow, because we need to flood everything to everywhere, it becomes critical from the scaling perspective. Okay? So this flooding is not very good. As well, we have periodic reflooding, so refreshes. And again, when we have very, very big network, it can be problematic because it means we constantly refresh the information, reflood the information. What are the examples of routing protocols that are using this concept? Very typical that we use currently in the network. Yes, OSPF, ISIS. In times is ATM world, we use PN9, Trill. In L2 we have Trill or Air bridges, not very frequently used, but OSPF, ISIS, basically this is what you have today from this one. Another protocol type that we are using is distance vector or path vector. Okay, so what's the difference here in distance vector, path vector? Well, the difference is here that instead of flooding all the information to everywhere, I receive the information from my neighbor. I process this information. What does it mean process? I have some policies, accept this, doesn't accept this, maybe manipulate some attributes, and add distance, so add metric of the link that I received from the neighbor, and re-advertise this post-process prefix or pro-process information to my neighbors. So this is, in BGP, instead of manipulating the network, we're manipulating the AS path attribute. Yes, we are adding some AS numbers into AS path. So that's the reason it's path vector as well. So it's good from scaling perspective because we can scale such network to very big sizes, but it's not very good from convergence time, from the speed, because at every node we need to process this information before we resend this information to my neighbors. Okay, so convergence is pretty slow. Typical example is BGP, maybe RIP, someone is using, or IGRP. This is the typical example for such networks. Here's comparison between the speed of the link state and distance vector. So as you see here, in the link state, I receive the information from the network, from my neighbor, and I immediately flood this information. And then later on, I can make some local computation, how to calculate the SPF, next hop, etc. So which means that the speed of the propagating the information is quite fast. I fastly propagate the information. In distance vector is different. I receive the information, and here I process this information. So I manipulate my I manipulate my BGP attributes, for example. I do some policy checks, etc., to allow this prefix, not allow this prefix, etc. And it takes some time, of course. And after processing this information, I send to my neighbors. Why I'm discussing that? Because every of these protocols has some advantages that we can use in the DC fabric and has some disadvantages. So the new protocol will take the best, what is the best from the existing protocols, and put this in the new protocol. Right, what is the current state in the DC routing? Well, we have two approaches, basically. One is based on the BGP. So we try to make some enhancements to BGP to adjust better into DC environment. Okay, so basically very frequent, or when we talk about BGP, you could imagine we can run single hop external BGP sessions between the node. Every node has different AS number, and basically we effectively replace IGP with BGP. Could be BGP LU. And there are some challenges with that. I will not go here in the details. Another option is use some ISIS with some extensions as well. So improvements for ISIS, for example, to run DC fabric. Well, it is good. Both of these options are good if the DC fabric is not big, particularly big. But if we start to think about DC fabrics that have like 100,000 nodes in the hyperscale cloud environment, there could be challenges here with this one. So to address the challenges, you could have some centralized fabric director, yes, to overview entire fabric. So it requires some external server or external controller to control the DC fabric. Or we could have some new protocol that addresses the issues. So here is a small summary of the issues, for example, that we can face. So let me just put a couple of things. Like here, for example, high degree of ECMP, equal cost multipath or non-equal cost multipath. Yes, high degree, I means here 100, for example, ECMP. Or here, for example, introduce a new node without disruption. So there's overload bit that we have in ISIS, and so on. So let's discuss, because I have a couple of things to discuss with the Rift itself. So let's discuss the Rift. Let's start to discuss the Rift. All right. So basically, the Rift, the idea of the Rift, as I mentioned, is to take out what is the best from the link state protocols and from the distance vector protocols, forgot the disadvantages, or design the protocol in such a way that we don't use these disadvantages that were present in this link state or distance vector. So basically, we have the new protocol is combination of link state and the distance vector. Okay, so we have link state in the north direction. So from bottom to top, so from south to north, in this direction, this protocol behaves as link state. Okay, this is the idea. This is the major statement. And from top to bottom, in the south direction, this protocol behaves as distance vector. All right? So basically, so what does it mean here? So here, when I go from top to bottom, in general, I advertise only default route. Because in general, for this guy here, on the bottom of the network, for him it's enough to have default route, because he can do load balancing. In that case, he do load balancing between two things, two neighbors, and send the traffic to two upstream neighbors. Okay, simple as this guy doesn't need to maintain full routing table with 10,000 prefixes if my network here is 10,000 nodes. Okay. Again, this is true if the network is structured. Yes, if the network is structured in this way, like we see here on the picture, which is typical for DC. And as well, this is true if there is no network failure. Yeah, because we could imagine that there is this link failed or some link here in the failed, and maybe if you use only default route, we will create black holing of the traffic, because we would assume that I can send some traffic to some upstream node, but this upstream node lose the connectivity to his upstreams. Okay? But this is the initial assumption, and then we will see how we address the network failures in this structure. Okay, so basically, this guy from the top to bottom, we are sending only 0, 0, so default route, and sometimes we are sending some more specific routes, but again, not full routing table, not 10,000 routes, but some, not 10,000 routes, but some only specific required to avoid black holing, too much, to avoid black holing in the, to avoid black holing during network failures. And maybe we have some kind of traffic engineering, we'll discuss that later on. And the fourth, so we are using combination of these two, so link state and distance vector. The fourth, which is not used in the current protocols, is something that we call bounce. Okay, so basically we are bouncing the information. So here, this guy, I received some information here. I am the green one, yes? I received from the red one some information, and I'm bouncing this information here or here. So I received from the red one, and bouncing this information to my upstream red ones. Why do we need to bounce this information? Or discuss later. Okay? But basically, here is I need to learn the network failures in my network, and this is used for the network failures in my network and for flood reduction. All right, so we have some PDUs as well, some packets associated with the routing protocol, as with typical routing protocol. So we have some packets, we call these packets topology information elements. Okay, it's not written here, but the packets, like in ISIS, we call it link state PDUs. In OSPF, we call it LSA, so link state advertisements. Here in Rift, we call it topology information elements, so TIA. And we could have some topology information elements that are used for the hello discovery, so we have automatic discovery. And the speciality of this protocol here, we have pod number, level number, and not ID. So not ID is not special. We use not ID in OSPF and ISIS, but special thing is level and pod. Yeah, So level, as I mentioned, this is structured network with different levels. So that's the reason we have level. And pod is point of delivery as well is used in data centers. Okay. We use that for the auto configuration. I will discuss that later on for auto configuration. If the level is not set or the level is 0, it means this is the leaf. This is the most bottom node in the network. All right, the requirements from the DC fabric guys was to have automatic discovery of the miscabling. So if you have thousands of switches and you start to cable these thousands of switches, it might happen that you miscable something. Okay, it might happen to you miscable something. And here we have built-in detection of miscabling. So basically, if you imagine here, you know this configure with this is level 0, this is level 1, this is level 2, and these nodes they belong to pod 1, these nodes that belong to pod 2. Then we have, for example, we don't allow communication between more than one level. So here's communication cable from level 0 to level 2. These guys, they will start to run these hellos, these TIs, and they will discover that they connected to the difference in the levels is more than one. And they said this is not allowed, so adjacency will not be built, and some SNMP trap or whatever error will be fired here, alarm that something is here miscabled. Here as well, so between the pods, communication directly between the pods is not allowed here. Yes, in the hello messages, we have pod number. So here, this guy will advertise I am pod number 1, I am pod number 2, is not allowed. So we have built-in protection against miscabling. This is very important. That was the request from the customers that are looking for that. Okay, then we have another set of topology information elements that is used to distribute the information about the network. Yeah, before it was hello, kind of hello. So this is kind of link state PDUs on LSAs. And we have two kinds of these information elements. One, what we called north TI, so what we set in the north direction. And another, what we called STI, what we sent in the S direction. Okay, because as I mentioned, north direction, we are behaving as link state. In south direction, we're behaving as distance vector. So there's slightly different set of information that we distribute. Okay, there are some attributes. I will discuss these attributes when we discuss the operation of the network. So this is most important, automation disaggregation. So this is example of the DC fabric. Okay, and as I mentioned here in the north direction, as you see here, I advertise my node ID. So every node has some ID. Need to have some node ID. So as you see here, 211, 212, 202, 201, etc. Every node has some node ID. I advertise this node ID. And as well, I advertise here the prefixes that are reachable through me. Yeah, so for example, node number 2, 202, you advertise the prefix D. That prefix D here, I prefix D is reachable over node number 2, over node number, node number 202, over node number 201, prefix C is advertised. And this is flooded upstream. So as I mentioned, upstream in the north direction, this is link state. So link state, we are flooding. Okay, so we receive this information. These two nodes on the level 1, they receive this information from level 0, and they're reflooding this information upstream. This is like OSPF or like ISIs, no difference. Okay. In the downstream, we advertise following information. We advertise who is the neighbor. So here, this guy has two neighbors. Yes, 111, 211. 111 is this guy, and 211 is this guy. So he advertised my neighbors are 111, 211. And as I mentioned, he advertised only default route. Okay, this is what he advertised. And here this guy is doing similar, yes? He has more neighbors because he has 31, 32, whatever, 101, 102. He has 4 neighbors. This guy has 4 neighbors. He advertised I have 4 neighbors. And as well, I advertise only default route. Okay. Now, this guy is doing bouncing. So I received, so here I'm 111. I received from the upstream this information. and without changing anything this information and bouncing to all my upstreams. Why do I do that? Well, I do that so that my upstreams knows who are the neighbors of the upstreams on the same level. This is needed to discover network failures. We discussed that just in a second. Okay, now we have some network failure here, so this link is no longer available. Okay, this link is no longer available. What does it change? Well, in the advertisement from 31, I see now only one neighbor, 111. Before, when I go to my previous slide, as you hear in the previous slide, it was two neighbors here, 111, 211. Okay, so now this 32, node number 32, knows, okay, I received a couple of prefixes here, prefix A, B, C, D, and these prefixes are reachable over these neighbors. So A and B is reachable over 111. 31 can reach 11 as well. So my assumption is that 31 received this information of these prefixes as well from 111. But 32 knows that 31 has no reachability to 211. And I have some prefixes here, C and D, which are reachable over 211. So now this guy, 32, is advertising still default plus C and D. Okay, and here these guys receive default plus C and D. What would happen if the 32 would advertise only default? Well, 111 would start to load balancing and would set some traffics, some packets destined to the destination C to this guy. And this guy would drop this because this guy has no information with destination C. Okay, this is what we call automatic disaggregation. So in normal case, we send on the downstream, we send on the default, but if some network failures happen in the network, we start to send additional prefixes. But again, it's not full routing table that we send downstream, just the prefixes that are exactly needed to avoid the black holing of the traffic. Okay. All right, I am time. Then another thing is the flooding reduction. So in ISIS or SPF link state advertisement, when I receive something from a neighbor, I flood this information to all my neighbors. Okay, so if you have highly meshed network like here, like our typical data center, it means here, yes, I am here the yellow router, I send this yellow information to my upstream neighbors, and these upstream neighbors, they send this information again. So basically this pure guy received the information 4 times, the same information received 4 times. If I would hear more than 4, yes, that like we have here 10 in one, that he would receive that 10 times. The same with the green information, yes, this guy is the green one, he advertised some information, and then it's reflooded to everyone. So again, these guys here upstream, they receive this information 4 times. Well, it is okay to receive 4 times or even 10 times, but this is not efficient. Yeah, it is enough to receive this information 1 time. Maybe for redundancy, for resiliency, if I receive it 2 times, that's okay. But I don't really need to receive that 10 times, yes, because it doesn't bring me any new thing. And why it's not good to receive 10 times? Because every time it's associated with CPU processing, I need to send this information, I need to accept this information, I need to process the information, etc., etc. And to process 10 times the same information, it makes no sense. All right, that's the reason in Rift we have optimization of flooding. And basically, so this is nodes and level L plus 1, L plus 2. Every node from the reflecting, you remember I discussed that information is reflector. So this yellow node knows who are the upstream neighbors of this node and level 1 from this reflected information. So this yellow node runs some algorithm to select, okay, I know that all these 4 nodes can forward me traffic to all my upstreams here, but I select only this one and this one to forward the traffic, and I tell this one, this guy, do not to forward the traffic. So basically this is the idea, and this is in the special bit. Yes, so here I send this yellow information with not this special bit set. Here I send this information with special bit set, which means these guys, they are not reflectors. only these guys are reflectors, only these two guys are sending. So we are selecting two nodes for resiliency, for redundancy. Okay? And this is discussed in the draft exactly how we select that. I will not go into details, but this is discussed in the draft. How is it selected? Perfect. So zero-touch provisioning. Another discussion, another request from the DC operators, DC fabric operators as well. What I mentioned in the beginning, if you buy new memory to your server and to your laptop, you just put this memory in your server, in your laptop, and you don't provision anything, you don't configure anything, so it's auto-provisioning extension of the memory in the server. So here's the same request here. So if you put some new switch here, it should be auto-provisioned, without any configuration. How we achieve that? So basically, system ID, so we need to have system ID. There are two options system ID at the moment. Either you manually configure, but if you manually configure, it's not auto-provisioning. So we can derive system ID from the Mac. So AU64. So every of these devices, we have different Mac. So we can derive system ID from this Mac. As well, we are prepared here, so we can misuse a little bit this Mac because we can. You can imagine that you would like to have multi-topology routing. So in OSPF, for example, we have multi-topology routing with Rift as well. We could have, so we can use these 24 bits. 24 bits for organization governing, 24 bits for multi-topology, different system ID for multi-topologies. Okay, then we still need to have some level of configuration, and the minimum level of configurations on the top switches, or the top nodes. So here, these top nodes need to be configured as a certain level. So for example, if I configure this on the level 3, I basically allow the DC fabric with maximum 3 levels. And this is my top level. But this is not the problem, because usually on the top level, we don't have so many devices. So most of the devices are on this level, level 0. So we'd like to avoid configuration of these level 0 devices. Okay? If you need to configure something here, it's okay, but again, it's only level. Or we have special flag, we configure the super spine, and then this level 16. And then these guys, they start to run this hello protocol, okay? And then E run hello protocol with A. A advertise I am at level 3. This guy has no level configured, so he automatically assumes a lower level, so level 2. Okay, so he will be automatically level 2. Then this guy still advertised here, and this guy again assumes lower level, and so on, and then we have level 0. So this is in short how the configuration, auto configuration works. And the last thing, and we will be on time, is automatic load balancing, weighted bandwidth load balancing in case of link failures. This is as well that was requested by some DC fabric operators. So basically, this is current situation. In the current situation, everything is symmetric here, so you have symmetric load balancing. Okay, so from node X, for example, when you send some traffic to node A, it could be load balance over I and J, and then it could be load balance on E and F. That's perfect. But now, let's check what happens if, for example, this link from E and E, so E and J, and this link fails. Okay, so we have some link failures here, and node X fortunately knows about these link failures because in these hello messages that are reflected here. Okay, so you remember we received the hello. So here is run some hello. We receive this kind of hello protocols, but this is reflected here. So this is reflected here, which means this guy will know we know the information about the status of this link, the bandwidth of this link, because this is encoded in these hello messages. And this guy X can run special algorithm, which is defined in the draft, and this to determine how the load balancing should be done. And here on X, so I am here on X. If I go over node node I see I have 2 times 10G. This is my local links here, 2 times 10G, and 2 times 40G, because I have 40G here and 140G here. So I have altogether 100G. This is the bandwidth on this level and this level together. Okay. Then if I go over node J, I have again 2 times 10G, and here I have 4 times. Yeah, 2 times 10G, 4 times 40G, so I have 180G. So this is the status that I know from the exchange information. And then, according to the current draft, we are determining exponent of 2 of this one. So here 100 is between 2 to the power of 6 to the power of 7. So this exponent here is 7 for this one. And 180, this is 180, is 2 to the power of 7 to the power of 8, so it's 8. Okay, so here the maximum exponent is 8. And based on this 8, here is the formula in the draft how to adjust the metric, the link metric. Okay, so basically the link metric is adjusted here. That I have my normal link metric adjusted with this formula 1 plus 8 minus 7. So this is double 2. And metric over J is not adjusted, it stayed there. And then, sorry. And then load balancing is based on this metric, so it's a reciprocal of this metric. So basically over I send 1/3 of my traffic, and over J, I send 2/3 of my traffic. So it's again automatically done without any traffic engineering or something like that. All right, so I will finish now. There's a couple of more things here. I will not go into details, but important here as well, we have a kind of overload bit like in ISIS. It is possible to have some lightweight RFT Rift version on the leaves, because on the leaves we don't need to have soft baud protocols. Yes, only north baud. So it could be cheap version of Rift. Okay, there's some special consideration for the east-west forwarding when we have direct links on the same level. I will not cover here, but it's described in the draft. And summary, let's discuss the current status, standardization status. So at the moment, Rift is the IETF working group draft. So it's not Juniper only draft, so to say. This is a big support from different vendors. As you see, Juniper Cisco is co-authoring this draft at the moment. And the working group lead is from Nokia. So there's support from 3 vendors, Juniper, Cisco, Nokia, and Alu. And Comcast is as well is co-authoring the draft. So Comcast is one of the biggest service providers in the US, is co-authoring the draft. So work is progressing pretty well, I would say. And as well, coming soon, IETF Rift Hackathon. So if you have Python skill scripts, you can participate in the implementation of Rift, or participate to know more details about Rift. Because at the moment, we have implemented that as pre-production code, which can be run on Linux or OS X. So you can run virtual topology with this Rift and learn how does it work. We still don't have that in the real product. Right, thank you very much. I know it was a little bit long, but that's the new protocol. Thank you.
Any questions? I assume this is pretty much new for the majority, so no.
Yes, did you heard about this protocol already or not? It is the first time you're hearing that. No, okay. Well, as I mentioned, this is mainly DC IP fabric focused, and some enterprises which follow as well the structure of DC IP fabric network structure.
Thanks, Krzysztof.
Okay, thank you very much.
Final.